which are subgroups of GL and R or GL and C, and most of the classical subgroups have algebraic condition like saying that O transpose O equal to 1, etc. Or we had index notation, which was that Oij, then we Oij, Oik equal to delta Jk. Something like this, etc. Because we had the unitary things also. So if you want, I write U dagger U equal to 1, U dagger U. And most interestingly, we also had a geometric interpretation. Which is for orthogonal groups they preserve the Pythagorean metric. Or let us just say they preserve a Gaussian metric. And a special example preserve delta metric. Okay. So writing it as if it is some symbol, metric delta, a matrix which is simply Pythagorean. For Lorentz group, we introduced the metric 1 minus 1 minus 1 minus 1. It is SO31 in the algebraic sense. It preserves metrics of 3 plus signs and 1 minus signs, and we write the metric to be eta and the algebraic or index notation is lambda mu nu eta mu sigma equal to times lambda sigma rho equal to eta nu rho. So that is the index notation for the Lorentz group lambda matrices, or abstract matrix notation geometric statement is that these lambda matrices times eta sorry for it looking too baroque, but this, and of course we here there are many more subtleties. It's not enough just to say determinant equal to +1 or -1. One has to worry about the sign of the time component versus signs of these, and it's a little more interesting, this group, because one is space inversion, the other is time reversal, and the discussion is a little long. So for the time being we just write these things. And finally we did the symplectic groups, which were SP2N, SP2N, and I think I didn't write any R or C in it. We just call it SP2N for the time being. We will not be interested in SP2NC, so automatically R. And we introduced here a metric epsilon, which is of the form block diagonal plus and minus 1. It runs along the diagonal. The classic example of this is that in classical mechanics, well, it could be either, because structurally they are both the same. We have either the Poisson brackets, which we say QA QB equal to 0 equal to PA PB, A equal to 1 to N, but we also have the requirement that QA PB are equal to delta AB. So this amounts to introducing psi which is equal to, which is from the list, so as a set, okay, set equality, equal to Q1 or P1 or Q2 or P2, and here mu will then go over 1 to 2n. So make these the new coordinates, Q1, P1, Q2, P2. Then essentially these Poisson brackets, so maybe I put here this for clarity, because curly brackets are used by a lot of people. So as Poisson brackets, so the Poisson bracket relations essentially become a symplectic metric. On this so-called phase space. And canonical transformations are the ones that preserve Poisson brackets. So the canonical transformations are essentially, they form the symplectic group. I think we wrote the detail last time in symbols. I will not repeat it just now. So constitute sp2n. So that is what we were doing, and this gives the example of the canonical transfer of the symplectic group we did last time. So now I will move on to something much more practical and direct before we come back to slightly more formal things. So now we begin with SON or SO3. Example come further developments. So let us begin with rotation group. So sometimes we also call it rotation group instead of SO3 when we actually have the physical meaning in mind. Rotation group preserves the rigid length. I don't know whether I wrote it here or not. I spoke something like that. So yeah, preserve a Gaussian metric, but specifically it preserves the Pythagorean length, the distance between points. So it rotates rigid rods into rigid rods. So preserves rigid bodies. What we are now going to do is try to understand some interesting aspect of this group, which is to show that if you know the infinitesimal version of the group, then you know everything about the group. So this is a very, very powerful statement, and I have put it as a theorem in quote marks right now because I am just saying something that is intuitively understandable but not a precise statement. This is essentially what is called Lie group theory. This is at the heart of and that is essentially the second half of this course. It is Lie group theory, and we will start with SO3 as an example and SU2. So we start with SO3. A typical example is rotations around the Z axis. So Z axis does not move, so that remains 0, 0, 1, and here we write it out in terms of an angle, minus sine theta and cos theta. And so let us call this RZ theta. We can similarly write out RY phi and then R X psi. This is all completely temporary notation. I mean the angles we are using. So what should we be writing here? Can you fill this out? The main point to remember is that by our conventions, if we have minus sign in the upper diagonal for Rz, We also retain minus sign above the diagonal for Rx, but for Ry we have minus sign below. Okay. So this happens because of choice of right-handed axis, essentially choice of right-handed axis. So once you choose x, so several points I want to make here of mainly of convention and how we think about these. So we should have a right hand screw rule working, so we can put x, y and z. So that is the correct orientation. Of course, in this figure it is difficult to see this, so this is going away from us. Okay. So if y is going away into the paper, then this forms the right-handed system. And then there is the issue of active versus passive rotations. Okay. So this writing minus sign for Rz is one convention. The other convention is to write plus sign and minus sign for Rz. Of course, you have to do the same thing for Rx, and then for y it will flip. But let us think of what is active rotation, and I am actually doing it in front of you. So let us see what we get. So suppose we restrict to xy axis and take a genuine vector. So we rotate a vector, not the axis. So the difference between so-called active rotations and passive rotations is whether you rotate the axis or you rotate the object. So if I have this vector v and if I rotate it to a new position, by an angle theta, then what I find is that x component, so I don't want to clutter the diagram too much, but there is Vx, Vy, there is Vx, we can just say V and V prime. Okay. This vector is V and its rotated version is V prime. Then we can see that Vx prime is less than Vx. This is how I remember things. Okay. If I rotate, then Vx prime is less than Vx. Now I look at this matrix, the Rx matrix, and ask, is the x component going to reduce or increase? And sorry, yeah. So rotating about Rz, so I look at this matrix and ask whether the Rx component is going to reduce or increase. It reduces provided I put a minus sign here. Okay. So because I will have put here Vx, right? So Vx prime is going to be found from cos theta minus sin theta 0 acting on Vx, Vy, Vz. So Vx prime is going to be equal to cos theta times Vx and minus sin theta times Vy, and the example vector we have taken is all in first quadrant, so all components are positive to begin with. So this is going to reduce the Vx component, and therefore this is what I call active rotation. I have rotated a vector. And one more matter of convention, of course, it is an active counterclockwise rotation. Somehow we have all accepted that counterclockwise is the correct thing. Apparently in England you can actually buy clocks that go counterclockwise, which would be good to have on the wall because keep everyone confused. So but somehow counterclockwise is standard. So, active counterclockwise rotation would lead to this choice of signs. Now, let us look at the infinitesimal version, that is where all the interesting story begins, and I am sure you are familiar with all of this. So, Rz, if I have a small angle delta theta, it becomes equal to 1 minus a half delta theta squared, right, dot dot dot. Then the sin theta, which is a minus sin theta, becomes minus delta theta plus dot 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 0, 1, then delta theta here, this remains the same, 1 minus a half delta theta squared dot 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 and 1, 0, 0. So, if we ignore the quadratic things, then it is the identity 3 by 3 identity matrix, and then plus delta theta times 1 0 minus 1 1 0 0 0 0 0 0 plus order delta theta squared, which we are going to ignore. So, the infinitesimal version suggests this matrix which has no numbers in it, it is just ones and minus ones, and it is antisymmetric like this. Similarly, we can check that. So, this we call L subscript Z. And we can also write out Lx and Ly. So, you can try to write it in your book. It is x rotation, then all this will be 0. It should have same sign as Lz, and Ly will have zeros here. So, we designate our matrices Lx, Ly, Lz, which capture the infinitesimal rotations in the yz, zx and xy planes respectively. Okay. So, I think it's important to write this, because later you will see some interesting matters of convention that come out of this. The capture infinitesimal rotations in the x, y. Here the order of this axis is important. Okay. So, z, x, y, x, y, z and y, z, x. Now, if you restrict yourself to only z axis rotations or the xy plane rotations, then the Lz matrix is enough to capture everything. Okay. So, now we note the property probably need to look at it a little bit. What is Lz square? This row into this column equal to -1. This other things are 0. This row into this column is also -1. What about Lz cube? Well, these are minus signs, so it is like minus the identity matrix Lz square. So if I cube Lz, then I have to take Lz square times Lz, so essentially put minus signs on that. So it is 0 plus 1 minus 1 0 0 0 0 0 0, which is equal to minus of Lz. But now you are all experts to note that this is exactly what the trigonometric series does. Square, cube is and with minus sign and so on. So Rz theta is actually equal to 1 plus theta times Lz to the n and minus 1 to the so theta times Lz to the n over n factorial. Okay, so what am I saying? So, well, so if you look at the full Rz, it has cosine thetas and sine thetas. So what I am claiming is that this property of Lz, that it oscillates in sines, it will become Lz, Lz cube becomes minus Lz. So Lz to the 4 will become just Lz, because Lz square is anyway equal to minus 1 and 1. So Lz to the 4 will become, sorry, plus signs here. So in the upper corner, the alternating even powers are plus and minus 1s in this corner, and the odd powers are the same as Lz, again fluctuating in sign as you go 1, 3, 5, etc. Right? So if you just raise this to enough powers with theta supplied, you will just recover cosine and sine theta series. So Rz theta is just equal to the power series theta Lz to the n over n factorial and a 3 by 3 identity matrix added. This, so knowing the infinitesimal Lz, so this we sometimes denote symbolically as exponent of theta times Lz, where this is now a matrix exponent. And the exponential of a matrix is defined by its power series, and the power series is well defined because it is just matrix multiplication n number of times. So this is a matrix exponential. So at least as far as rotations in any one plane are concerned, they are just exponentials of corresponding infinitesimal rotations.